All right, so today what we're going to look at is atomic emission spectroscopy. And specifically, we're going to use different, most of these are chloride salts. I'll explain them as we get there. But really what we're looking at is the individual energy transitions in different metals. So most of these are going to be balanced as a counterion with chloride. It's not going to do anything. It's going to be the same in all of them. So really we're specifically looking at that metal. And what's really interesting, when we add energy to that metal with this propane torch here, you're going to see unique colors inherent to that metal. And ultimately, what that is inherent to the energy level transitions that you see. And once those transitions occur, we relax that electron, it emits a photon, and we see a color. So without further ado, let's look at a few of these. So the first one we're going to start out with is actually not a chloride salt. It's an acetate, so we're going to look at lithium acetate specifically. What does this lithium color look like? So basically, what I have here is a Q-tip with some water on it just to pick up this salt. I've got our lithium acetate here. I'm going to move it over into this propane torch flame. When I do that, just here, you'll start to see this sort of red, kind of violet color emitted from there. And that is inherent to, we're putting energy into our metal, and as it relaxes, as those electrons relax, we get an emission. And that color is sort of this red color we see. The little bit of yellow flame that you see in there is actually from the Q-tip burning. So sort of ran out of juice here. Let's move on to our next salt. So we're going to jump down in the periodic table. Now we're looking at sodium chloride. This is just normal table salt. I would reckon that almost everyone has this in their house. I don't advise trying this at home, but just so you know, this is what this energy transition looks like in sodium. So same thing, when we put that in here, we get this sort of very bright yellow color. And again, if we think about our electromagnetic spectrum, really think about the wavelength between sort of our red light, between our blue light. We're going to sort of move down there. And what does that mean, right? How does our wavelength change? And really, with that change in wavelength, how does that relate to the energy that these transitions or these colors that you see represent? That's pretty melted there. The next one we're going to look at is potassium chloride. So jumping down a little bit further on the periodic table here, should be similar, right, to our sodium. That's what we would expect. But actually, right, we kind of get this purple color out of it. And what that should indicate is that, well, maybe there's a little bit more energy here. I don't know if you guys can see it that well, but because it's kind of the same color as the blue that we get from the torch, but it is a violet purple color, a little bit more energy in that transition. And part of the reason for that is there's higher energy levels for this particular atom, or the electrons in this atom, to occupy. Next up, we're going to look at calcium chloride. So moving over in the periodic table, let's see what we get. Hopefully, we would expect a similar color, but let's see what we can see here. We don't see that, right? So now we kind of got, it's got to melt a little bit first, but sort of an orange color, really not on the red side, more of an orange color. And a lot of this then now, what we're talking about specifically is how are our electrons filling those orbitals? How do the electrons exist in those orbitals, right? And this is a huge piece as to the colors that we see. But what else I hope everyone's picking up on is that all of these colors, we haven't seen enough of them yet, but are really, you can use them to actually identify this particular metal. And in early chemistry, this was one of the ways that they did that, is try to figure out what was part of what. And you still use similar techniques to this in advanced spectroscopy to try and identify what the metals are, because those transitions are inherent to them. This next salt we have is copper 2 chloride. So hopefully you can see this is the only one that's not white. But what does that mean? How is that going to show up? Well, as you would expect, that color, you might actually end up seeing it again. You get kind of this green, emerald, maybe even a tint of blue in there. This is actually a salt very common in fireworks. To get that green color, it burns really nice, very indicative of the copper that's present there. Cool thing about copper, it's now a transition metal. But again, it still behaves like all the other metals that we have. So pretty cool green flame there. It's honestly one of my favorites. From there, we'll move to our last one, which is strontium chloride, the highest atomic number that we have here. And let's see what we get from our final salt. Hopefully a little bit different color than we've seen before to keep our trend going. And sure enough, it looks very similar to that red we saw earlier, but I would say, if anything, a little bit darker in color, right? And one of the cool ways that you can take this to sort of the next level is if you look at any of these lights through a prism, you can see distinct lines of the wavelengths that are being emitted. And I think we lost all of our salt here, kind of melted off, but yeah, one of the really, really cool things, if you can isolate your metal in a salt, put it in some kind of clean burning flame, and you get to see some pretty neat colors. And that concept is used really throughout chemistry to try and figure out what's going on.